What's up, guys? My name is Michael Lin. Welcome to my YouTube channel. Today we're gonna continue upsolving 660. At least I think it's 660. Yeah, it's 660. Okay, let's continue upsolving this. Hold up, real quick. We only have 3 more problems to go. So let's upsolve 660. All right. Let's see. Letter C. Okay, this is a long problem. Okay, I'm guessing it's a graph problem based on this. Damn it! I just looked at the problem tags. Okay. Let's see. Uncle Ben is Flint. Today told you his country's happiness. There's N cities, N-1 roads connecting each city. 1 to N. 1 is a capital. Okay. There are M citizens in the country. P of I live in the city. All of them are working in the capital. Okay. Everyone has a mood. Somebody leaves the workspace in good mood, but somebody are always in a bad mood. Moreover, any person can ruin this mood anyway. In the town, if a person is bad mood, he won't improve it. Now, the happiness detectors say that in each city, they want to monitor the happiness of each person visiting the city. Director of the ith calculates the happiness index H of I as the number of people in the good mood minus the number of people in the bad mood. Happiness detector is still in development, so there's a probability of making a mistake. One evening, okay, so one evening when all citizens successfully return home, they ask one to check the correctness of the happiness indexes. Yada yada. Can you do the same? Okay, so more formally, you need to check: is it possible that after all people return home for each city I, the happiness index will be exactly H of I? Okay. For each city, the happiness index will be H of I. Okay. So I didn't actually get any of that. What I'm gonna do is I'm gonna read in these values first, and then try to go back to that first. Let's see. Is anyone in the chat right now? Just out of curiosity. During this contest, I actually didn't solve any of the problems in this contest. I did do I didn't solve any problem in this contest. I did upsolve for the first 2 though. If you watch last live stream, If you watch the last live stream, I upsolved those. But yeah, now let's continue upsolving C and D. So, yeah. Let's just delete this. This was part of another contest. So I did another virtual contest the other day. So, yeah, I'm trying to increase my upsolving. All right, so we have to read in N and M. So number of cities, number of citizens. Let's read in P. Okay, so let's do this. C in N M. And then let's create a P with N values. We have to read in all of P. Okay. Then yeah. Each PI is between M0 and M. Okay. The sum of all of them is equal to M. I didn't know that. Then we need to read in H, so let's do that. Let's create a vector of H. Is that the same thing as size of A? Yeah, okay, so let's do that. Okay. Let's loop you here. Okay, and then once we read in H, real quick, let's read in N, M, H. Okay. Now what? Just go to happiness. Okay, so now the next N-1 lines contains the description of the roads per line. Each line contains 2 values, X and Y, where X, Y are cities connected by the ith road. Okay. So now we're gonna read in X and I. Let's see. X is hold up. 2 integers xi, yi. Xi and yi are cities connected by the ith road. Okay, so that's just reading in a graph. Let's see if we could create a graph. So if we're going to create a graph, let's do vector. Let's call this G for our graph. Actually, just call it graph. I think you normally index it from 1, right? So if there's let's see, n minus 1 roads. So we're gonna do n plus 1. Just because there's n minus 1 roads. Okay. Let's loop to n minus 1. Okay. Now what are we gonna do? We gotta read in each graph. Read in x, y, and then push back. So like at graph at x, push back y. So we're gonna read in x, y. So let's create x, y right here. So this is gonna read in our graph. So for every, what do they say? For every xi and yi are cities connected by the ith road. So yeah, so let's think about how you're gonna create this graph. So if we're gonna create this graph, let's look at this. From city 1, 2 and 4 are its 2, 4, and 3 are its neighbors. So let's see, 2, 4, and 3 are its neighbors. Yeah, so we're gonna do graph at I dot pushback y. So we're gonna do graph at x dot pushback. Do they have values? Do they have weights? That's a big question. Are there weights on this graph? I'm guessing they're not. Is graph weighted? Okay, I'm gonna assume it's not weighted, so then we're gonna just push back y. And then graph at y, push back x. So that means that y's neighbor is x and x's neighbor is y, right? Because like if we're gonna do here they input these nodes, 1, 2, 3, 4, 1, 2, 3, 4, no, 1, 2, 1, 3, 1, 4, 3, 5, 3, 6, 3, 7, 5, 11. So there's no 11 here. It's weird. Oh, that was a different one. So yeah. So up to 3, 7. So 1, 2, 3, 4 are the ones that are connected to the neighbor 1. And let's see, is 2's neighbors? Let's see. 2's neighbor is also 1. Yeah, so that's right. Okay. 3's neighbors 5 and 6 and 7. 5, 6, 7. Yeah, okay. So yeah, I think that's what we're doing here. I think this is ideally right. So now we write in the graph. Now this big question is, what are we gonna do now? Okay, so we need to check if all the places have still bad moods, right? Let me check the chat real quick. Hi, will I solve F? If I can solve F. We'll see. We'll see if I could solve F. If I can't solve F, then I don't know. Let's try. All right. Okay, back to the problem. Print yes if the data is correct. No. Okay, so the M cities, P of I people live in the ith city, but all of them are working at the capital. At evening, all citizens return to their homes using the shortest path. Okay. So there's M citizens in the country. P of I people live in the ith city, but all of them are working in the capital. At evening, all citizens return to their home using the shortest path. And we might have to use dextras or DFS or something. We have to use something. Every person has his own mood. Everyone leaves the workplace in a good mood, but somebody is already in a bad mood. Moreover, any person can ruin his mood on the way to the hometown. If a person is in a bad mood, he won't improve it. Happiness detectors are installed in each city. Monitor the happiness of the person who visits the city. The detector in the ith city calculates the happiness h of I as the number of people in the good mood minus my bad mood. Okay, so h of I is good mood minus bad mood. Let's say for the simplicity, the mood of a person doesn't change inside the city. Okay. Happiness detector is still in development, so there's a probability of mistake in judging a person's happiness. One late evening, when all the citizens successfully returned home, government asked them to check the correctness of the happiness indexes. Did he solve the problem? Can you do the same? So you need to check, is it possible that after all the people who return home for each city I, the happiness index will be equally exactly to HI? How do you calculate the happiness? They said good mood minus bad mood, but what does that mean? Their aims. Somebody leaves his workplace in a good mood, but somebody is always in a bad mood. Moreover, any person can ruin his mood on the way to the hometown. If a person is in a good mood, he won't improve it. Happiness detectors are installed in the city. You need to monitor the happiness of each person who visits the city. Detector of I city calculates the happiness index H of I as the number of people with good mood minus my bad mood. I don't understand. Let's look at the test cases. Okay, so two test cases. There's 7 and 4. So there's seven cities and there's 4 citizens, right? P of I is the number of people living in the I city. So let's see 10111010. It's the number of people in the I city. This is the happiness of this city. H of I is calculate happiness index of the I city. Okay. Let's look at this again. Okay. All citizens are in the capital. Let's describe possible scenarios. So all citizens are in the capital. So all 4 people are in the capital at 1. Right. Person from city 1, he lives in the capital, is in a good mood. Okay. Person city 4, he visits cities 1 and 4. His mood was ruined between cities 1 and 4. How do you know that, though? What does that mean? What does it mean by city was ruined? Is it because he had to move? Let's see. Okay, if somebody leaves his workplace in a good mood, but somebody has always in a bad mood. Any person can ruin his mood on the way to the hometown. If a person is in a bad mood, he won't improve it. P of I's people live in a city, of all of them work in the capital. All at evening, they use the shortest path to return to their home cities. Happiness indexes are installed. The detector in the I city calculates happiness index and number of people in a good mood minus bad mood. A person's mood doesn't change inside the city. Okay. When all the citizens go ask to check the correctness of the happiness. Can you do the same? Okay, so let's say he starts at 1. He lives in the capital, so he's in a good mood. He goes to city 4. Person from city 4 lives in city 4. He visits 1 and 4. His mood was ruined between 1 and 4, so he's in a bad mood. Person from city 3 visits cities 1 and 3 in a good mood. Person from city 6 visits 1, 3, 6. His mood is ruined between 1 and 3. In total, h of 1 is equal to 4 minus 0, which is equal to 4. What? H of 2 is equal to 0. H of 3 is equal to 1 minus 1, which is equal to 0. Yes, h of 4 is 0 minus 1, which is negative 1. H of 5 is 0. H of 6 is 0 minus negative 1, negative 1. H of 7 is 0. This is a first case. It's possible. Second case of the first test. 1, 3, 4 to 5. 1, 3, 4, 5. Oh, this is the second case. First case of the second test. What is the second test? This one? 1, 2, 1, 3, 1, 4, 1, 3, 5. 1, 2, 1, 3, 1, 4, 3, 5. Okay, yeah. All people start in a bad mood. This is the only possible scenario. If all people start in a bad mood, let's see, 1, 2, 5, negative 11, negative 2, negative 6, negative 1. I'm not sure what to do, actually. Negative 11, negative 2, negative 6, negative 2, negative 1. How did they get this? Are they going to explain? 4 minus 0 equals 4. 2, 0. 1 minus 1 equals 0. 0 minus 1 is negative 1. 0 minus negative 1 is negative 1. 0. Huh. Not sure. Let's see if I don't know. I'm not sure. Not sure. I don't know what they mean by this. Okay, so let's say. Okay, so we need to check if all the correct data is correct. So that means that it's possible to create the happiness index. So if you start out happiness with 4, he's in a good mood. Because his city, he doesn't leave, right? H of 1. The guy in living at 1 doesn't leave, so he minus 0 is still 4. So that's right. H of 2 is 0. Because his happiness is still good. Because he moves to 0. Okay. H of 3, you start at 1. Let's see, H of 3. 1, 2, 3. Started at 1, you minus 1, you get to 0, so it's possible. H of 4 is negative 1. So you start at 0, minus 1, you get 4. Okay, so what I'm guessing is that each of the weights to move from one place to another is going to be a minus deduction, so you get unhappy. So if you want to check if it's possible to get to the certain locations, right? So let's say if it was, want to see if it's possible to go to 4, 0, 0, negative 1, 0, negative 1, 0, that this happiness is right. At the current city, we should start out as, like, if it's positive, hold up. So we need to calculate, assuming there's a minus 1 weight for every distance from the root. If we were to calculate minus 1 for all of these from the root, use depth first search to calculate how far it is from first node to all the other ones. And then that would give us the distance it would take for that. So, yeah, so like if I start from H of 1 to H of 1 is 0, so I don't have to subtract anything. My happiness, I could just stay the same. So it's possible to get for happiness of 4. The H of 2, let's say I minus 1. Okay, if it's 0, then it doesn't matter. Like, we know, if it's 0, we know it's true, right? Because we only could subtract our happiness, I think. Right, yeah, we only could minus the number of people in bad mood. So if I'm going from like in this case, if I'm going from to 1 to 2 and h2 is 0, I could minus. I don't have to minus anything because the start is 0. So yeah. We should only check the ones where they are not 0. So like if it's like h of 1, h of 3, h of 4, h of 6, right? So like h of 1 to h of 4, we should check if the number is actually if the number is actually starting from if it's not 0, like, so in this case h of 3 is, wait, hold up, let's see, what is h of 3? 0, 1, 2, 3, 1, 2, 3. Oh wait, h of 3 is 0. Crap. Oh, but that doesn't matter because, I mean, if it's not 0, that's not what we should look for. We should look for the ones that are not 0. So like 4, -1, -1. These are not 0. Right? So like if these are not 0, we should check if it's possible to get there using deduction, -1 for each path. So like if I start for here at 1, it's definitely possible because like I'm not gonna. If I start at 4, because what I'm assuming is that to get from one node to another node, we're gonna subtract 1, minusing the mood, right? So if we were to get the shortest path for all the nodes using dextras, right? Assuming oh wait. No, we need dextras doesn't work with negative edges. Oh boy. Okay. Depth first search. We use depth first search for every node until we get to finding the shortest path for all of them using -1 for each edge, right? And we add them up. So like this one would be like 1, 2. For 5 would be -2. So then for each of those, if it's the ones that are not 0 for h of I, we check those. So right, so like 4 is not 0, so we're gonna check that. -1 is not 0, so we're gonna have to check the ones 1, 2, 3, 4, the fourth node. -1. Can we get -1 from here? Yeah, we can. 0. The possible is 1, 2, 3, 4, 5, 6. 6. Can we get -1 to 6? And I think that is possible if we do 0 and then -1. Like we didn't change the -1. Yeah, 0, -1. So yeah, let's do that. So let's call DFS on every single node, and then find the weight of each of those. So yeah, let's do that. I'm gonna do it recursively because that's the only thing I know how to do actually using DFS. So actually for h of I, we should index it at 1. The reason why I'm indexing it at 1 is yeah, h of I and p of I we should actually index from 1 because the input values are actually indexed from 1. So let's actually do that. So we're gonna do this. Yeah. Hope this doesn't bite back later on. But yeah, now we're gonna call DFS on. Let's call DFS on the graph. I'm gonna make graph a global variable actually, so that I don't have to deal with the whole passing the crap in over and over again. So I'm gonna do that. Okay. Here, then I could do, this is a good hack you could do if you want to set a global variable. You call your graph and then set it equal to vector. Yeah, this is technically a constructor for setting your global variable. Yeah, you could do that. Then we're gonna call DFS on. Hold up. I'm gonna have to call DFS on every single node. So how many nodes are there? There's n nodes, so I'm gonna call DFS on every single node. And then call DFS. So if I'm going from, we're starting from 1, and then we're gonna go from 1 to the current value, and if it's Yeah, we're gonna calculate negative edges for every single one of them. All right. So like here, in this case, 1 to 1 it would be 0 because like you're not going anywhere. 1 to 2 will be -1. 1 to 3 would be -1. 1 to 4 would be -1. 1 to -1 to 1 to 5 would be -2 because it would go 1 2. 1 to 6 would be -2. 1 to 7 would be -2. Yeah. So we're gonna do that for all the nodes. Get the DFS. Go check if it goes to the nodes. Yeah, that's what we're gonna do. We actually need a visited. Here, hold up. Okay. We actually need an array of visited actually. Yeah, I'll just call it a bool vector bool visited. Pass this in. Visited at current is equal to true. So at the current node, we're gonna set true. For every neighbor of the current node. First of all, I gotta pass in the current node. Yeah. So visited current node. For every neighbor of the current node. So for every neighbor of the current node, we have to call DFS. If it's not visited, we're gonna call DFS. If not visited, call DFS on the neighbor. Yeah. Okay. Call DFS passing in visited, and then neighbor. So we're gonna call neighbor on DFS. Then after that, we're gonna. What are we gonna do? So let's see. I need to draw this out actually. So let's say we call DFS on 1. Right, we start at 1. We need to get from 1 to 1. That's actually not going to take anything. But let's say we start at 2 now. To get from 1 to 2, our graph is going to have, let's say, one's neighbor is 2, 3, and 4. So that's what our adjacency list will have. 2's neighbor is, what is 2's neighbor? 1. 2's neighbor is 1. 3's neighbor is 1, 5, 6, 7. Okay, 4's neighbor is just going to be 1. 5's neighbor is just 3. What's 6 neighbor? 6 neighbor is 3. 7 neighbor is 3. Okay. So if I call DFS, passing in 1, for every neighbor that's not visited, we're going to visit that. So for 2, so we're going to go to 2, and 2's neighbor is 1, and that's already visited, so we don't go to that. Yeah, we don't call DFS on that. So we pass in 1, 1's neighbor is visited. Okay, so in 2, 2's neighbor is not visited, so that's it. That ends there. It would come back to the loop. It would go to 3. 3's neighbor, 1 is already visited. Yeah, 5, it'll go to 5. So it goes 1, 3, 5. 5's neighbor is 3, already visited. So yeah, that would be the end of that loop. 6, okay, so hold up. It's not visited, we call DFS again. If it gets to here, let's push the current value to add 1, I think. Yeah, we also have to check if it's not the parent, I think. I know like when you DFS recursively, I think you have to check if it's not the parent also. 1, 2. So we're not going in circles. But I feel like, but when you said visited to true, I think that's fine. Yeah, so here, what we're going to do, we actually need to pass in like the current length. Because we're going to each of them we're gonna add 1 every time. So let's pass in like current weight, and then we're just going to do weight plus 1. Right. After this DFS, let's just push back the weight to the current weight. So like I'm actually gonna create like weights for this. So let's create a variable weights. See, what are weights? So what are good weights? Yeah, I'm gonna create a yeah, I'll create a boolean vector weights. Okay. Weights is gonna equal to n plus 1. Okay, so that's that. At the end of this, because it's not gonna it's done with all the neighbors, we're gonna add weights to our current weights. So, damn, this should be cur weight. Yeah. So then our total weights is going to equal at cur weight. Current node is gonna be the current rate. Cur weight. Yeah. So once it's done traversing the current, for all our weights at the current node, we're gonna set it at its right weight. Okay. Ideally this should work. I'm not sure though. So yeah, that might actually give all the weights to become they're all positive, right? Because we're adding 1. And we could just set them all to be negative afterwards. Actually, it really doesn't matter, because like we're gonna subtract it anyway. Anyway, it's DFS. Did I do a visited? Crap. Okay, I'm gonna create a visited boolean visited n plus 1. Visited current node current weight. Okay, so visited current node current weight. So what's the current weight? We could pass in 1 for the current weight, because then we could do 1 plus 1 plus 2. Actually, should it be 0? Let's see. If we start at 0 plus 1, that'll be 1. That'll be 3. Yeah, it should start at 0. Current weight should be 0. Yeah. Okay. Yeah, this should be where this should work. I'm not super sure if this works or not. So yeah, I'm not super sure. But if it does, ideally it should give us weights for all these, like 2, 3, 2, 1. That's what it should give us. So let's copy this. Let's do 1 test case for now. So let's do 1 test case, and then we're gonna do 7 for these. Yeah, the first test case. So it should give us here. Okay, let's see if it actually does what it wants us to do. So set true. Okay, not visited. True. Yeah, it doesn't doesn't go back to 1. Okay, so the current weight at 2 is going to be 1. So to go from 1 to 2, it would go to 1. Yeah, that's right. So from 1 to 2, it goes to 1. Okay. What neighbor is this now? What neighbor is this? Neighbor's 3. Okay, so now we're at 3. Let's see. 3 should go to 1 or 5. So it shouldn't go to 1, it should go to 5 after that. So here it should not go to 1. Wait, did it go to 1? Hold up. Visited. Neighbor's 3. I don't know what's going on actually. Hold on, let's go again. Calls DFS. What is the current route? Okay, so it goes to 3. Yeah, so I didn't actually go to 3 yet. Yeah, my bad. Go to 3. should not go to 1. So it doesn't go to 1. It's going to go to 5. Yeah, so now it's at 5. Does it go to 5? What's 5's neighbor? 5's neighbor is 3. It doesn't go to 3. And this should set to 2. Yeah, current weight should be 2. So from 1 to 5, from 1 to 6, it should be 2. Wait, no, 1 to 5. 1 to 5 should be 2. Yeah, so that's that. What's the next one? I just completely lost track. Oh, 3 to 6. 3 to 6. So DFS on 6. Doesn't visit 3 because we already visited 3. Sets from 1 to 6. From 1 to 6, the current weight's 2. Okay, so that's right. Let's see our weights. Okay, so from 1 to 5, it's 2. 1 to 6 should also be 2. Yeah, so that's good. Let's see. It should go to 7. Yeah, it goes to 7. Sets it true. 1 to 7 is also 2. Let's see. Yeah, 1 to 7 should be 2. 1, 2. Okay. And then it's done with 3. 3's neighbor. Does it go to 5 or 6? Let's see. So 3's neighbors are done. What is this? Current weight is 1. 1 to 3. Yeah, 1 to 3 is 1. Okay, so that's right. Okay, I forgot what neighbor are we on? We're on 4. Did we visit 4 already? 4 should be 1. Okay, visit 4. 4's neighbor doesn't go there. Okay. Okay, so let's see. Not graph. Where's the weights? Oh my gosh. So 1 to 4. Okay, so I think we visited all of them. 1, 1, 1, 2, 2, 2. Yep. So 1, 1, 1. 1, 1, 1, 2, 2, 2. Okay. Yeah. Why am I giving -1 for each edge? So what I'm doing is I'm calculating the depth of each node from 1. Right? So then remember they said the happiness is determined, like you only could get rid of happiness. I think that's what they said. So like if you're in a bad mood when you leave the city, you get rid of a bad mood, right? Happiness would be exactly more than H. So yeah, like if you're in a good mood, but someone's in a bad mood, so you could ruin on the, but any person can ruin his mood on the way to hometown, right? So like if I'm starting from here, and I'm in a bad mood, let's say I'm in a bad mood from here, I'm always gonna deduct bad moods, right? Because you only could deduct bad mood from leaving your home, from leaving from 1. So that's what we're doing. We're calculating the depths of each node. So yeah, that's what this is. Then after that, we're gonna loop through for all the ones that are not zeros and see if we could actually get H of 1 for all of them. The happiness for each of them. That's what I'm planning on doing. I'm not sure if this is right though, because like from the tags it says DFS and similar, but there's also DP and greedy, and I don't know how you're gonna solve this DP way. So yeah, that's what I'm doing. I'm calculating the depths of each node. Yeah. Yeah. So now after that, should be done. Okay, we actually don't need to call DFS on the other ones because we're always starting at root 1, so we don't actually need that. So we don't actually need this for loop. So yeah, just calculate all the depths, each of them starting from 1. Now we need to see if can we get the right happiness based on the depths. So right here, So you could only move, like you could change your mood when you move from one city to another, right? So if the end happiness is 4 0 -1 0 -1 0, the ones that actually change are the ones that are not 0, right? Because like if my happiness is 0, no matter what I move, I don't have to deduct my happiness when I move, right? Like if I start, my happiness is 0, I don't have to deduct every time I move down. Like it's optional if you don't know what their happiness is. So if it's 0, I don't have to check that, right? So I'm gonna check the non-zero happiness. So yeah, for each of 1, I think if it's non-zero, it's possible regardless. Like, I don't think you could get negative happiness if you start from 1. Is that valid? Do I gain happiness when I go back? Do I gain happiness when I go back? I don't. Okay, I'm assuming once you go to your house, okay, so I'm gonna assume that when you start at 1 and you go down, you're not gonna come back up, right? Because you're already at your hometown. Like if you live at 1, for H of 1, happiness at H of 1, you're once you go down, you're not gonna come back up. You're not gonna go down. That's what I mean. You're not gonna leave your hometown because for H of 1. So I'm guessing no matter what, H of 1 is always gonna be fine. Okay. Yeah. So then let's check H of 3. To go from H of 1 to H of 3, we're going to subtract. We're gonna subtract. Yeah, we have to subtract the depth. So that will be that. Yeah. So what I'm gonna actually think of doing is actually going to be for every happiness. I'm gonna loop through every happiness, and I'm going to add by the depth. And if it's greater than 0, you're fine. If it's not, I'm going to say no. Yeah, so that's what I'm going to plan on doing. Because remember, we only could lose happiness whenever we go downward. So if I add the depth, the happiness to the end results, and the happiness are all negative, I think that would not work. Right? That means that their happiness is not impossible. Right? I think that would be impossible. So yeah, I'm gonna do that. If that doesn't work, then I don't know. I'm gonna look at the editorial because I think at this point, how long have we been live streaming? I'm just rambling at this point. How long have we live streaming? 43 minutes. Okay, yeah, I've been rambling for 43 minutes. So yeah, I don't want to like completely just ramble on so long and so forth. So yeah, I'm gonna go through every depth. I'm gonna go through every happiness and I++. So I'm gonna go through every happiness of what was it, H? Yeah, H. So I'm gonna take H of I plus the weight of I. So remember we calculated the depth of each node. I'm gonna do that. If it's greater than 0, then continue. If it's less than 0, I'm gonna say it's impossible. So I'll do possible is equal to true. If it's less than 0, I'm going to say possible is equal to false, and I'm going to break. That's what I'm going to do. If it's equal to 0, it's fine. So if it's greater than or equal to 0 is also fine. So if possible, then I'm going to still print out yes. Otherwise, I'm going to print out no. Okay. Yeah. Okay, I'm going to test this out now. Okay, so we have yes, yes, no. Yes, no. Wait, the second one also possible? Why is it possible? How is this possible? First interval, first test case, second case of first test. Yeah, how is this possible? Wait a minute. Second case of the first test. Why is there output? Yes. 1, 1, 1, 2, 3. 1. Oh wait, 1, 2, 1, 3, 1, 4, 3, 5. All people have already started in bad moods in the capital. This is the only possible scenario. So if you all start in bad mood. Oh, okay. So if they're all negative, then no matter what, it's fine because they all start with bad moods. Okay, so that's a simple test case. Because if they all start in bad moods, they're all going to be negative. Let's see. So I'm going to do a Boolean check when I read H. So I'm going to do like all negs equal false. So then if an H is positive, all neg is equal to, okay, all neg is equal to true. If we find one that's positive, we say all neg is false. Yeah, that's what we're doing. If all neg is, if it's possible, or all neg, not all negative, we're going to print out yes. Yeah. So yeah, I think no matter what, if it's all negative, I think it should be fine. So yes and yes. Okay, let's try this one. Should give us no, no. No, yes. Okay, what is the problem with the last test case? No, there's no way to achieve the given happiness in both cases of the second test case. Why? They're all positive. 13, 1, 4. 13, 1, 4. Can I get... Why is 13, 1, 4 not possible for 1, 2, and 3? 13, 1, 4. Let's see. Okay, so 13, 1, 4. Can I get 13, 1, 4? Happiness. No, you cannot. Because if I start from 1 and if my happiness is 13, I'm going to remain at 13, so yeah, that's possible. If I start from, if my happiness is 2, I could get to 2. I could get 1 because for 2, my happiness is 2. Subtract 1, I'll get 1. Why is it not possible for 3? My happiness is 4. I could have a happiness of 5. Minus 1 to get 4. Hold up. His mood was ruined from 1 to 4. City 4 was ruined to 4. Yeah, because you deduct happiness. Why is the last one impossible? Why is that the case? Alright, in another, how long have I live streamed? I've been live streaming for 49 minutes. Alright, if I'm still can't figure it out, I'll look at the editorial in another 10 minutes. So I'll put like 10 minutes on the clock. Yeah, okay. Pretty sure this is possible though. Why is it not possible? Because 13? But if you're always in a good mood, 13 minus 1. One. If my happiness is 2, then I could do that, right? Happiness is 2. Let's look at this test case again. So they subtract 1 from 3, h of 3. So you get 3. Still could get 0. Yeah, if you start 1. Let's reread this question again. Hmm. 13 minus 1, 4. Why is 4? Why can't I do 4? Maybe that's the problem. You can't do 4. Come from 1 to 3, 4. But happiness. What if there's 5 people that are happy? Only one of them is ruined. Why is that not possible? You can have 4 though, right? Unless they're saying like the total happiness, it's impossible given the weights of the total. Oh, are they talking about the weights, the total weights? Wait, let's see. 1, 2, 3, minus 3. No, but in this case, the each depth was minus 1, minus 1, minus 1. Right? They didn't minus their happiness of 4 people. If you add up the values that they subtracted, it doesn't equal to 4. Right? So it's not based on people's like each person's. Oh my gosh. There's M people sitting there. Each person has its own mood. Somebody leaves his workplace in a good mood, but somebody is already in a bad mood. Moreover, any person can ruin his mood on the way to the hometown. Yes, I know that. If a person is in a bad mood, he won't improve it. Okay. So if we have so if you have negative bad mood, he's not going to improve it. Happiness stickers are installed. So the happiness is the number of good people minus number of bad people. Like if I don't know. Let's just submit and see what happens. I know it's not going to pass, but I feel like it's definitely possible though. Yeah, so number 2 we got wrong. Because why is this not possible? 13, 1, 4, 3, 3, 7. Wait, what is 7? 3, 3, 7. Hold up. Whoa, what is 7? 3, 3. 7 nodes. Wait. No. 3, 3. What am I reading? What are we reading? Hold up. Am I missing something? 3, 3, 7. 313. Wait, what is 313? Hold on, I think I'm missing something. 337. So we have 13. 313. 13 is the number of Wait a minute. 13. Number of citizens. Oh. Oh. Oh, okay. Okay, so there's 13 citizens. Oh. My fault. If there's 13 citizens. Okay. If we're subtracting the depth, we need to. Okay. That's probably why it doesn't work. But let's look at the first test case. If there's 4 citizens, let's say there's 4 citizens. Okay, all 4 are fine. 2 is fine. 3. One person goes from to 3. One person goes from 4 to -1. So these are not good. So one person's a 6. But that doesn't write. The depth would be 2 -6. Well, yeah, that's assuming if you didn't get unhappy from here. So you have 0 -1. So that'd be 2. 7 would be saying that. Do we have to check how much you deduct each citizen? Okay, so 4 people start here. And we're going to each 1, 2, 3, 4, 5, 6. No, but that doesn't make sense. If there's 6 cities and each of them there's only 4 citizens, how is that possible that you could go from here to all of them? H of I. I don't know. What do you guys think? Anyone in the chat? Try to use the information how many people lives in a city. How many people lives in each city? Okay. Maybe you're right. Whoops. Okay. Yeah, I didn't even use that. Number of people living in either city. I have to draw this out. Okay, so if wow, this got even more complicated. I thought this was complicated before, and now it just got even more complicated. Okay, I have to draw this out. Okay, let's see. One person lives in one city. One person lives in one city. One person lives in. One lives in one city. So there's so one person lives in. Wait, hold up. Let me see. P of I is the number of people living in the ith city. Okay. So in this case, there's one person in the first city, one person in the second city, one person third, one person in the fourth. So we need to see if is it possible to can you move from one city to another? If I take can I take the person living in third city, put that to 6? Can I do that? Do they all stay in the same city? Wait, no, hold up. Let me go back. So M cities, P of I lives in, but all of them work in the capital. At evening, all citizens return to their home cities using the shortest path. Okay, Okay, so we're gonna use the ones that are currently living in the same city. Oh, my fault. Ah, that was 10 minutes. Damn. Just when I'm trying to get through to this. Yeah, I'm going to actually look at the editorial now. Damn. I think I'm guessing you have to use the idea that there's people living in each city. I didn't take that into account. So I think that's the reason why my code failed mostly. But let's look at the editorial now. I don't need the solution. For each city, count VA of V, how many people will visit it. Knowing this value and the value of the happiness HV, we can calculate how many people visited the city in a good mood. Why are you dividing by 2? So for each count A of V, how many people will visit it? How many people are going to visit a city V? How many people are going to visit city V? So for 3, how many people are going to visit 3? Then we got to count the value of the level of happiness, then divide by 2. So we could single out 3 criteria for the correctness of the values of the happiness index. AV plus HV is a multiple of 2. For each V, G of V is an integer. Yeah, okay, we know G of V is... how many people is in a good mood is an integer. Yeah, we definitely know that. Like, it can't be... You can't have, like, 2.5 people in a good mood, right? G of V is between 0 and A of V. Number of people who pass the city in a good mood is between 0 and the number of people who would visit the city. Yes, that is true. Sum of the people in a good mood from 1, 2, 3 up to K is going to be less than or equal to the one visiting the city. The good people in the city. What? This is not telling me anything. For each city V, count A of V, how many people will visit it? How many people are going to visit the city? Knowing this and the value of the level of happiness, we can calculate how many people will visit the city in a good mood. So how many people are going to visit the city? So let's see, how many people are going to visit the city? So like, let's start from, there's 4 people. Let's look at the first case. So here there's 4 people, and there's 1 person at the first city, 1 person at the 1, 2, 3, third city, 4th, 5th, and 6th. So 1 person at 1st, 3rd, 4th, 5th, and 6th. Okay. How many people are going to visit that city? There's 1 person who's going to go to 4. 1 person who's going to go to 5. 1 person is going to go to 6. Right? Yes. So add up the happiness of the city, which is 4. Didn't I do that? Right. Wait, no, I added up the depths. Wait, but this doesn't tell you. Okay, so let's you add up and divide by 2. Wait, what? Okay, screw it. Let's look at the solution. Okay, so he did use DFS. But what I don't get is what is going on. Okay. Yeah, you could do this with Ancestor. Okay, set the... What the hell is A? A is a number of people going to the city, I think. How many people will visit the city? Okay, so that's equal to the number of people in the city. Yes, okay. We're going to sum it up. For every... For every neighbor, call DFS on it. we're going to sum G2. What's G2? What the heck is G2? What is G2? G2. What's that? What is G2? G add equal to G at 2. What is G? What is G? I don't know what G is. Sum of G is going to equal to G plus equal to G2. The good people at the city. Then we're going to take the total people and add equal to A at 2. If it's equal to mod 2 is equal to 0, that's first. If it's not, we're going to set axis equal to false. We are going to divide G of V equal A of V plus GH of V over 2. What is going on? I'm going to copy this code and see what they're actually doing, because this doesn't seem right. What are they doing actually? What are they doing? What are they doing? Retracted. Letitia, did you solve this problem? Or is anyone even watching? I'm not even sure if people are watching it. We've gone to 1 hour. Okay. So yeah, I'm gonna copy the code and just run through it because I don't know what they're doing. I know they're running DFS, but I just don't know what they're doing at this point. They're adding what is this? G of 2? What is A of 2? Like that doesn't make, I don't know what that tells me. Okay, let's copy this. I feel like we were close, but I mean, things happen, so yeah. We were very close. So let's do the same thing what they did. So they do DFS. V is just the current node, so I'm actually going to write current ancestors away so that you don't have to. If you do ancestor, I'm guessing you don't have to do a visited because then you don't have to. Okay. They said to calculate A, which is the number of people visited. So I'm going to actually create a so yeah, I'm going to take this out. I'm going to take this out also. We don't need a visited node, but we don't need weights, but we need A and P, right? We need, what is P? Oh, we have P. We need, what do we need? A and G. So we need visiting city, number of people visiting the city, and we need good people in good mood. People visiting the city in a good mood. So I'm going to write that. Excuse me. So let's do that. Let's do okay, why did I do that? I just still need to call DFS. Okay, so we need good people. That's going to equal vector n plus 1. And then we need people visiting city. So people visiting city. So I'm using good variable names because I don't understand the code. So So let's do this. Let's call these, make these global, so then I don't have to deal with this. Vector good people. We don't need weights anymore. That was just depth. But let's see, people visiting the city. We need this. Yeah. Okay. So let's see what we're doing. Okay. Set the initial people visiting the city to the people at the current city. So people visiting city is going to add current at the current city is going to equal to the people at the city, current people at the city. Well, what is this? But I did that. Oh, yeah, I have to make these two global variables also. Okay, I gotta do the same thing. Okay, so now we have that. Okay, people. Okay, so now we need a sum variable. 0 int 2. So this is like the each neighbor. So I'm gonna do that for every neighbor at the graph at the current. If the neighbor is equal to the ancestor, continue. Okay, so we don't need that. We don't need that. We could just say like if it's not equal, then just do this. I don't like continues. Call DFS2 with a neighbor, and what are we passing in? What's V? Oh yeah. Call DFS, passing in the neighbor, and then the current becomes the ancestor. Okay. Yeah, this is actually good. This is a hacky way of using, instead of using a visited node, a visited array for DFS. These guys are on a roll. Okay, then sum G plus equal, sum of good is going to add G of neighbor. I don't know what that is. Good. So is G G of 2. People visited. Oh, so G of 2. G is good mood. People visit in a good mood. Ah, okay. So that's good people. People visiting at the city that is in a good mood. So we do good people. We sum up the good people, their neighbor of that. Then we're going to sum up wait a minute. People visiting the city? Is that what A is? Yeah. How many people visiting the city? Then we're going to sum up city at the current node is going to equal plus equal people visited to the city at the neighbor. And then why do we divide by 2? People visited city at current plus the good people in the city. What's H of V? Wait. Oh, that's happiness. Happiness of the current. Mod 2 is equal to 0. Huh? What is this for? Okay, if it's... I don't know what's this for, but okay. This is ugly code. We could just do say not equal to 0. Then do access equal to false. So they have a Boolean variable of... So possible equal to true. Well, let's create a Boolean possible is equal to true. And then they say possible is equal to false. Then they sum up the people visiting the city. The good people at the current city is now equal to the sum of people visiting the city at current plus current at h. And divide by 2. Okay. Why do we leave half of them? If it's greater than what? I don't understand. If the good people is greater than 0 and the good people is less than or equal to the number of people visiting the city, then it's good. Otherwise, it's false. So if the good people is greater than 0, greater or equal to 0, and the good people is less than or equal to the total number of people visiting the city, it's fine. Otherwise, it's false. It's not possible. So if it's... Why can't you just check if good people... if it's less than 0... If it's less than 0 and... Or... the good people is greater than the thing, then say false. So yeah, let's make that. If good people at current is less than 0, or good people at current is greater than the people visiting the city, the current city, then we set possible is equal to false. If the sum of the good people is less, if it's greater than the current good people, at the city, then we set pos equal to false. Okay, this is I don't know what they're doing. If this works, I don't know. I actually don't know what they're doing. I know they're using DFS, but besides that, I'm not so sure what they're doing. But if it works, then it works. And let's try reasoning it out. Let's read the tutorial again. Oh, whoops, I forgot. I forgot to print yes or no. If it's good. Pos is equal to true. Pos is equal to true. And I reset this. Graph at I resets this. Okay. Let's see. Yes. Okay. I just don't understand the logic where they got it. What problems did you solve during this contest? I didn't solve any problem during this contest. Yeah, I didn't solve any problem during this contest. I did upsolve the previous problems though. So during this contest, I did terrible. Yeah, from yesterday. Now that I realize what I did wrong though, I think it's all good. See, okay, I don't understand the solution. I just copied and pasted it. I don't understand, like, what is going on? Okay. What is going on? Okay, let's go back to the editorial. So you could count the number of people visiting it and the level of happiness. You could single out 3 criteria for the correctness of the happiness. It has to be a multiple of 2. This I understand. Because good people can't be... It can't be like... It has to be an integer, right? For each city, number of people who pass the city in a good mood, it has to be less than or equal to the number of people. The good people have to be less than or equal to the number of people visiting the city. Okay, I understand that. The sum of all the values going from one city, the good people going from one to the other one, it has to be less than or equal to the number of good people. Okay, that I understand that also. I don't understand the code. Let's go through it. Okay. Let's go through the code. All right. I'm going to create a breaking point of, whoops. Oh, we don't need all neg anymore. We don't need this. Let's go through it. Okay, so let's say we have the first test case of, let's just try 1, 4, 7, all these. This. So 1, 7, 4. 7, 4. Okay, so this is the number of people in each city. This is the happiness where we're checking if it's possible or not. This is the every neighbor and the graph of every neighbor in every city. Okay. Damn it. I didn't put a breaking point. No. Try again. Hold up. Okay, did I do it? Yeah, okay. Let's keep going. Keep going. Okay, let's DFS. Okay, we start at 1. How many people are visiting the city? So at value 1, the number of people in city 1, people visiting the city is going to equal the number of people at city 1. Okay, so that's just going to be 1. So people visiting the city is going to be 1. At city 1 is going to be 1. Yeah, so people visiting city is going to be 1. Sum is 0. Now for every neighbor of the first city, so that's for every neighbor of first city is 2, 3, and 4. So we're going to go through 2, 3, and 4. The neighbor is not the ancestor. So yeah, we're going to go through 2. Okay, so now how many people are visiting the city 2? That's going to equal the people at city 2. People at city 2 is 0. So it's 0. Sum is now 0. Now, what are the neighbors of city 2? Neighbors city 2 is nothing, so it's not going to do anything. Okay. This is where it starts getting weird. Okay. Gotta check if the people visiting the city plus the number of the end happy people is an integer, right? You can't have a half people, right? So I think this would be fine. Um, we are going to take the good people. We are going to add up the people visiting at city 2 plus the people visiting. So the people at, okay, so the good people, okay, current city is 2. We're going to add up the people at the current city 2 plus the happiness. So the happiness at current city 2 that we're trying to check is 0, right? So that's going to just give us 2 plus 0 over 2, which is going to give us 1. But let's look at something again. Let's look at this again. So yeah, they're just doing this because it has to be an integer. So, this is just like a check to make sure it's an integer. You know what I mean? So yeah, that's what they're doing here. So the number of good people is going to have to be an integer, so they add them up and divide by 2. Now we have to check if the good people that we just added from the people visiting the city with the people at this with our happiness at the city. We have to check if it's between these, right? So the people visiting, so if it's not, then it's false, right? Okay, and then now we need to check if the sum of the good people is greater. So if the sum of the good people is greater than the good people at the city, then that's false. Then you can't do that. So what is our sum currently? Our sum is 0. So yeah, it's not gonna do anything. Okay. What is the sum of our good people? So what is the good people that we have was 2, right? Wait, let's see. What do we sum? Our neighbor is... Oh, we have no neighbors. Do we have neighbors? Wait. What's a current neighbor? Current node is 1. Ancestor -1. Neighbor's 2. What's the good people at 2? 0. Okay. So you're still going to get 0. What's the number of people who visited the node? People visited the city at the current city is 1. So do we just add 1? Okay. So people visited at 1 is now just 1. Let's see. People visit city. Yeah, it's just 1. It didn't change. It didn't do anything. Okay. What's a neighbor now? 3. DFS on 3. 3's neighbors are... I wrote it down. 3's neighbors are 1, 5, 6, and 7. So we're checking on 1. What is the ancestor of 1? Oh yeah, okay. People visiting the city is now equal to the people in the city. So the people in the city are now 0, I think. How many people were in city 3? Oh, 1. There's 1 person in city 3. Sum all the good people. 3's neighbor. We already visited that. 5. DFS, we're going to go to 5. How many people are in 5? Let's see, how many people are in 5? I should be using very good variable names to explain. 5, 0. 0 people in 5. Some of the good people. Nothing. Okay, now we gotta check if the good people are actually in the right bounds, so that's fine. Good people is going to equal to the people visiting in the city plus the happiness divided by 2. People visiting the city plus the happiness at the city divided by 2. Then we sum up the good people, sum up the people visiting the city. So how many good people are there? Wait, what is sum now? Sum's still 0. Yeah, there's still 0 people. People visiting the city at current. How many people visiting at the neighbor, though? 0. So there's going to be 1. Okay. Okay, how many people are in the city now? I feel like this is like a really hacky solution. You know what I mean? Because what they're doing is that because they know that good people has to be an integer, they add up the people visiting a city and the happiness that they gave us, like the one where we're trying to check if the happiness is possible, divide by 2, and then they do all this stuff, right? And then they keep going doing that, summing up the good people, right? Because to get this solution, it was basically this part where you have to assume that good people visiting a city in a good mood is an integer. So that's why you're able to add up the people visiting the city plus the end happiness over 2. And they do that over and over again. Each time they do that, they check if it's in between the boundaries of the actual people at the city. Right? And they make sure it's an integer, a multiple, and they make sure that this works. And they keep going. So that's basically, I think that's what this code is doing. I don't. Why do you guys want to know my handle? My handle's trash. I'm literally a beginner, guys. I'm literally a beginner. So like, I haven't actually been like solving that much problems. So, yeah. If you really want to know my handle's Michael Lin 250. I mean, I don't really do anything here. I mean, you could send me a message, I guess, for what problem you want me to go over. But, yeah, my handle's right here, Michael Lin 250. Okay, back to this. Let's see. Yeah, so that's what they're doing. Like, I feel like to get this solution, you had to just guess that you had to assume this is true. Like the number of good people has to be a multiple of 2. It has to be divisible by 2 because you can't have like it has to be an integer. You can't have like 3/5 of a people, right? And that's this assumption you had to do that. So that's what they did, and that's what they're doing here. For every city, they add up the people currently visiting at the city with the final, the happiness that we're trying to check at the city. And then they set that equal dividing it by 2. Because they're assuming that the good people are always an integer. Right? Because you had to have guessed that, you have to have made sure that was the case. And then they check the boundaries. Like if it's less than 0, it's not possible. If the good people is less than 0, it's not possible. If it's greater than the current people visiting the city, it's not possible. If the sum is greater than if sum of good people is greater than the actual good people at the current city, also not possible. So yeah, that's what they did here. I'm not sure if I could actually code this up myself again. The sum of the good people has to be less than the current. Yeah, if the sum of the good people is greater than the current people at the city, you can't do it. All right, guys. I'm gonna end the live stream now. Sorry, Arun. He showed up the wrong time. Yeah. I'm gonna end the live stream now. Yeah, it's easier to understand with 2 DFFs. One calculates the number of people who visit the city, and the other one validates H. You might be right. I don't know what that means, though. So A is equal to good plus sad. Yeah, I get that. H is equal to good minus sad. Yeah, I don't know. I don't know. This problem requires two major leaps. Basically, the number of good people has to be an integer, and that's a leap. So that's when you have to realize it's an integer. So yeah, we assume it's an integer. Then we have to add up. We add up the current people at the city, visiting the city, plus the happiness, and divide by 2, right? Because it's good people. Number of people at the city is good people minus good people. So happiness is good people minus sad people. So the number of people with good people is going to be good people plus. Happiness is good minus sad. So then good people is going to be happiness plus current people visiting plus, and then dividing by 2. So you had to do know that. And then this is just making sure it's checking the right boundaries. So yeah, that's basically what they're doing. They're going DFS, going through every single node in the tree, and then they're going to sum up the good people, and then they set the current good people based on the happiness plus the people coming in, and then they check the boundaries. If it's not possible, they say it's false, right? And the boundaries are basically the total good people can't be greater than the people arriving, right? And it can't be negative, right? You can't have negative good people, and that's what they're doing, and they keep going through that until they reach all the nodes, and then if it's still possible, they return yes. Yeah, so that's basically this problem. I might give a better detailed explanation later on, but yeah, I'm gonna end the live stream now because it's like 1 a.m. Hope you guys enjoy this live stream. You could hit me a message anytime you want. Rate, comment, subscribe. I'll check you guys later. Peace.